Thank you everybody for joining us today. We are here for Sketchulation Part 4 tutorial for new users. My name is Natalie C. I am a structural engineer at Tipping Engineers. We are a firm in Berkeley. We've been around for about 41 years. Joining me today is Mike Korlick, who is one of our principals. Mike is the mastermind behind Sketchulation. We're delighted to have him here. Today, we are going to go through an example for 2D structural analysis, and we're going to spend some time kind of viewing the options for plotting results. But before we dive into part 4 tutorial, we are actually going to do a little bit of a review. I apologize for all the text, but we just wanted to share all of this with you in advance so that you understand what we're going to review. So I'm going to pass this over to Mike.
All right, thanks so much. I will share my screen and we'll dive in. Alrighty, by way of review, if you'd attended last time, then you saw the tutorial on fiber sections. We drew a few different column types. We used this command ccol, concrete column, and we entered some information here and drew some columns. And then we created some fiber materials. FM brings up the fiber material sidebar. And then we created a couple of different materials. We created a concrete material, and we typed in F'(c) for the strength of the concrete, which was linked to an expression outside of our material editor there. And then we made a rebar material. And we use the paintbrush to assign those things to the different shapes in rebar. We can always double check what's assigned by overriding the layer colors here. And then we did the fiber section analysis form. So I think we probably would do a PM diagram. So I type PM and that select my cross section, and that brings up the fiber sectional analysis form. And we went through a bunch of the options here. We're showing the reduced PM diagram, reduced by the code phi factors. We can click on a point on the graph and push the arrow keys and go back and forth along the PM diagram. And the data on the right is updating as we go along on different parts of the PM diagram. And we can select a fiber, and we can look at the fiber material and kind of see what's the material doing as we go along the PM diagram and get a good sense of the state of the cross section. We can look at the unreduced capacity if we're maybe doing an evaluation and we really want to know what's the expected strength of this cross section. It's much bigger. It's not reduced by the phi factors. And then we can also analyze the cross section at a different angle, say 45 degrees or 90 degrees, and rerun the analysis. And now we have PM diagrams for each of the different angles that we entered. So there's a 45 degree and the 90 degree option there. So we went through all that, and we reviewed how you can use this analysis, fiber section analysis form to really dig in and try to understand what your cross section is doing in a detailed way. But then typically for design, you'll have multiple cross sections, and the best way to get quick answers is to tag your cross sections. So we showed that you could draw several cross sections, and you can use the auto tag command. So I start to type auto, and there's the command auto tag, and we put in /call, and it created those tags for each of those cross sections. And then I showed that we can reference those tags in a table. And here we have a table here. We made a column called TG representing the tag. And I have my 3 tags there for my 3 column cross sections. And then I see these arrays here. These are being generated by an expression that is defining the symbol PM. And so that's defined over here. I define this expression for PM and use one of the special functions in the program, getPM. And the argument is TG. So in the column here, I can see that this is a global expression. It's taking its definition outside the table. and then it would be referencing this column TG, and it's generating the PM diagram in each one of these cells, and then also I have the reduced PM diagram. That's also defined by this other function here, getPM, built-in functions in the program. And so all the data is here. You can't see it because we're rendering the arrays compact, but I could show all the data if I wanted to. I say don't render the arrays compact, and there I see my PM diagrams all displayed on all their glory. But we normally don't want to see that, so then I just send it back to render the arrays compact. So we see that there's data in there, but we're not necessarily having to see it all. And then we went through a little bit of graphing, showed that you could make a series here. I created a chart, CHT, and drew that chart just like that. And then I started to type series, add series. And then I simply went to my table cells type of graph. And here's where I picked out the table that I wanted, which was table one. The name for the different graphs that I'm going to make is TG, and then the column with the data is FiPM. And I click add, and that generates all of the PM diagrams for everything in that table all at once. And of course, the PM diagrams are upside down, which is our convention in the United States is to flip them. So we can just do that by reversing. I select the chart and pick the axis Y options to reverse the order. And so now I have my PM diagrams, and then I showed you can edit the series. So I start to type edit, and you see here edit series. Also, there's two commands that get you the same place. EDS is what I always have in mind. And so these are my series. These are three different series that are all being generated by the same table. And so it's actually, in a way, it's both one series and three series. There's a master series that controls all three of them because it's all linked to the same table. And here I showed that you could do some, point labels, and we can say pick that we want to see the point label just at the maxima, and we can report the X and Y values from our chart with these special tags at the maxima, at locations of maxima here. And then you can also just get some help if you're not sure what the different tags are. They're explained here in this table. And I can't see that one point label, so I might want to expand that, and I can just select the chart and I start to type axis. Maybe probably better would be type maximum. And I want my maximum value to be larger than what it is right now. So maybe I put in 10,000. And I'm starting to see it. Maybe I need to make that bigger. I push enter again, which repeats the same command, 12,000. Okay, now that looks pretty good. So that's what we did last time, the fiber section analysis. Anything that anybody wants me to review on that? Any questions?
Mike, before we get started in the next
Hmm.
tutorial part, can you put the keyboard
Oh, sure.
on? Thanks.
Here we go.
Thanks.
Yeah, no problem. One thing I would point out here is that once I have my cross sections all drawn, I can export them to a DXF file. Select them. I type export, and I get to pick the base point of where I'd like the file to be created, and then it brings up my save as dialog, and I can put those wherever I like on my computer and save them there. So then I can go into AutoCAD or Revit and import those cross sections that I've drawn. Okay, if there are no questions, I will dive into the next part of our tutorial.
Perfect.
Okay, so the next thing that we wanted to talk about is structural analysis. Sketchulation has a lot of features for doing structural analysis that are going to be helpful in your day-to-day work. And basically, it works in a very similar way to the rest of the way the program works. So if we wanted to draw an element, we would type the command FE or frame element. I click that button, and now it's asking me for the first point of my element. Let's say I have a beam that I want to design. Let's say it's a 15-foot long wood beam. So I just clicked a point right here, and then I turned on my snaps F8. Sorry, my ortho angular constraints F8, and now I want to make this 15 feet long. So I type F 15, and then the apostrophe to tell the program that it's feet. And here's my 15-foot long beam. I want to have that take up a little bit more of the page, so I'll probably just reduce my annotation scale slightly, maybe reduce that to 48. Okay, so now I have a beam that's really taking up a decent amount of the page. Um, so what's the next thing we want to do? Probably I'd like to put a little label up here that says beam design and give that a heading text style like that. And now I'll continue with my analysis here. So I want to make some restraints for the two ends. We'll do a very simple beam, a simple span beam to start with here. So I start to type RES, and the shortcut is just R for restraint. And I put a restraint at the end, and then I hit enter, and that repeats the command. I put that at the other end. So now I have my two restraints. The two ends. Now let's say I have some distributed load, some dead load on this beam. That would be a linear load. I know that the shortcut for that is LDL, but as I type lin, may need to give a little bit more. There we go. Load linear right there, LDL. And then I'm just pick the two ends of the beam, and I've put in a linear load. Now let's say that this load is dead load, and I also want a live load, so I can select this grip here. Yeah, I can stretch that grip around just to kind of move it away from the beam, just for visual purposes. But I can also select it and start stretching it and push C to copy, and now it's going to make a copy of that loading. So now I have two linear loads on my beam. I know one is going to be dead load and one is going to be live load, and we'll define that now. Let's say I have a tributary area for my beam. I'll make a little expression, xt, and I'll say, b underscore trib. Let's say this beam is going to carry, I don't know, 5 feet of trib, like that. And then we need to define our dead and live loads. So let's say w underscore dead. Oops. Hit the caps lock. Dead is equal to, let's say this is 35 PSF for a wood building. And then I have my live load, W live is equal to 40 PSF. Okay. And so then the actual linear loads are going to be defined this way. I'll say W underscore D this time is equal to B trib times W dead. I'm pushing the tab key. Once I see the symbol that I want in the list, I just push tab to complete the list. And I can put my request for value operator and get the linear load. And then similarly with the live load, WL is equal to B trib times W live, like that. So I have my two linear loads. Now I double click into my linear load here, and I just put in W underscore D. It's the top one, so I push tab. That completes that. And then I double click on this guy, WL. And so now I have my dead and live load on my beam. Now we need to create load sets. So the way the program works, like a lot of other programs, you have a load set, and then you have a load combination. And this program extends other functionality to actually have load sequences. So in this program, you can, put the load in a sequence. So you're not putting all the dead load at once, or you're not putting the entire load combination at once. You can split it up. Normal design, you'd have the load sequence would be the same as the load combination, but we do offer that added capability for things like construction sequencing, or if you wanted to do a buckling analysis, you would increment the dead load until the column buckles or something like that. So there's some features for that. But creating load combinations from the code is pretty tedious. What we'll do is show here. I type ls, and that brings up the load set editor. I can make a new load set by clicking this new button here. And you'll see there are just a few options. There's some coloring, and then there's include self-weight or not. And I could make this dead if I wanted to. And then I could, and I would say include self-weight, and I can now assign that to my dead linear loading. And I could do the same for live. And then I'd have to go through and make the load combinations, LC, make a new load combination. Say I want this to be, 1.0 dead. I give it a name. And then I would go here to my load sets. It has a scale factor of 1. I click plus, and so now I have a load combination that I've made. And then lastly, I need to make a load sequence, LQ. And then this would also be 1.0 dead. And here I select from my load combination 1.0 dead. And I want to determine whether it has any special context. This is used for composite steel beam design. You can dictate whether loading is just for construction or not. Typically, there's no special context. We push plus, and so I'm going to apply all my dead load in one step. We also want to indicate whether this is a LRFD or ASD type of load combination. This would probably be, let's say, my ASD long term. And so now I've created a load combination, a load set, and a load sequence. And then I have to do this again for every single load combination in the code. But you have an easy button to basically auto create all these things. So I click on the wand here, and that brings up my load combination generator. And this is going to do a lot of work for you, so you don't have to define all those load combinations yourself. There's a bunch of check boxes here, options that you have for your own context, dead, live, roof live, earthquake, wind, snow, rain, earth loads. And then also you have, do you want LRFD and ASD or just one or the other? Do you want deflection load combinations? So these would be if you wanted just a live load combination. Then you have, do you want these plus and minus earthquake load combos? So if I had earthquake in here, this will generate negative E loads or negative wind loads. Create a construction load sequence. That's really only if you have composite beams, but that's there. And it asks if you want to overwrite things. And then you need this information for seismic. If you have, say, your vertical seismic load combinations, you have to include that. And you would put in an SDS factor, and it'll calculate those factors on the dead load that way. So let's say I just have a simple gravity beam. I select all these load combinations. I click OK. And what that did is it would have generated dead, but dead was already there. It generated live for my load set. It generated all these load combinations. If there was a 1.0 dead already there, it would have not overwritten it. It would just left it alone, or it would have updated it if anything was wrong with it. And then also it created the load sequences. So this is all done before you, for you. And you see here's one where I have my 1.0 dead that I named here, but then they also have a dead, which is the same. So I would just delete this one, not needed, and also I would delete this one, not needed. And the key thing here is also that it puts this context in, which is going to help the program know how to design beams and check DCRs and things like that. Okay, so I've got my load combinations all set up, but lastly, I need to assign these load sets to my actual loads. So I click the dead load, I push the paintbrush, and then I click my WD, enter, and now that's going to be considered a dead load. And similarly, I go up here to live, push the paintbrush, assign to live, enter. And now when I select these guys, it will automatically select in the list which one it belongs to. And again, I can override colors so that I can see which load sets these loads are on. Okay. Feel free to dive in and ask me any questions. Unmute yourself. I'd love to take questions along the way. So feel free to interrupt, but I'll just keep going. Yes.
Just one quick question. So
Yes.
The two editors you had, what's the difference between the load combination editor and the series editor? Like they look the same to me?
Yes.
Almost everything is almost identical.
Yes, exactly. Let me show you. So the load combination is a combination of load sets with load factors. So in this load combination editor, you're going to enter a load factor, and you're going to pick a load set, and you'll click the plus button to add something to this load combination. The load sequence is then sort of a sequence of load combinations. So in the load sequence, you're going to pick a load combination, and you're going to give it a number of steps in which to increment up to the desired loading. And so maybe a good example of this would be, let's say I want to put in my dead load first, and then I want to put in my live load separately. So what I would do is I'd first make a load combination that's live only. I type L. I go to my load set. I keep my scale factor of 1. Okay, and so now I have a load combination that is just live. And then I will make a new load sequence here. Dead. Say I put in my dead as 1 step. And I'll put in my live as 2 steps. Okay, so this is just the name of the thing so that I know what I'm doing. I can remind myself of what I've done. And then I go down here to my load combinations. So I'm going to put my dead as the first step. And then, so that's set up right there. And then I'm going to pick my live at the bottom of the list. I'm going to put 2 steps like that. And so now when this program runs the analysis, it's going to run dead load as 1 load case, and then it's going to run half the live load for the next load case, and then increment up the other half for the full. And then you'll be able to see results for each individual step. Does that make sense?
Oh yeah, that makes sense.
Okay.
Thanks.
I also have a
Yes,
question. So,
please.
can we change somewhere the code? Does it cover CSA Canadian code, or it's just for US?
It does not. That's something that has come up before, and I think it's something that we could do as an added feature. It's a good segue to say there is a user forum here, and if we had, let me pull it over because it's underneath. It's over here. So here's where you have a feature requests page. You can create a little account. It's a free account to make comments. This is where you could ask questions or report bugs or make feature requests. And if we had enough interest in doing that, I'm sure we could easily put in those other load combinations. But
I understand. So until then, is
yes,
it possible for me to
yes,
customize my thing? So because I saw somewhere in the forms that you have, for example, LRFD, ASD.
yes.
So the naming might be different, but can I just put, for example, the load combinations from the other code, or are there something from the codes that are within the programming and that I don't see and I can't change? That's actually my question.
Yeah, so this form is really a macro to generate load factors on load sets. So we use this terminology to because it's familiar with the American code. But if you had a different code, you would just change the load factors to suit your code. So I can do that even now. If let's say this load factor was slightly different in the Canadian code, I can click on it here, and instead of 0.75, maybe that's 0.85 for whatever reason that it's different. And so I push the paintbrush. It changes that load factor. I need to make sure and change the name because that is manually generated. And so now I've changed the load combination to suit myself.
Okay,
And then
great.
if you were doing this over and over again, you could actually create all your load combinations the way that you want them. You can save this as a template file,
Oh,
and you can then set this as your startup template so that they would always be there.
okay, great.
Yeah. Any other questions? Thank you for the feedback. Appreciate it. Okay, great. So where we are, we've created our load combinations. We've assigned them to the loads, and the last thing that we need to do here to get the model running is to create a frame element type. So I'm going to send these guys to the back, just the draw order, just so when I select here, it picks on the beam. So we're going to make a frame element type FET, and this brings up the frame element type sidebar editor, and I want to make a new cross section. And here we have a number of options to choose from. We have the AISC standard shapes that are embedded in the program that ship with the program. So I could also use generic, common shapes, but hand enter in the sizes as I like. I can put these are in inches by default because that's just to point out the units here. I bring up the layout editor and I can change units for for dimensions or for geometrical properties. Here I could choose metric if I wanted to, and then the default units would show up differently in these inputs. But I can always type in a different unit here. Let's say instead of 24 inches, maybe I make that 800 millimeters. It knows how to deal with that, so it does a conversion for you. And anyway, so this would be just a generic C shape. Then there's all the standard shapes that are in the AISC database that you have to choose from. And then let's see, we also have composite beam sections. That's a little more complicated. I'm not going to touch on that today other than to say that it's there. But the way that works is you first create your base cross section, like I say a W24 cross section, and then you come back and you make a new element type that refers to a composite beam, and it just has other inputs. Well, I can't do it yet because I have to make the AISC beam first, but we'll get into that maybe some other time in a future conversation. We have ACI, so concrete shapes. You can create a fiber section, draw a fiber section like we did earlier in the tutorial, and then you can reference it through a tag, and then use that for your analysis. And then here's where we want to get to in a second. This is our NDS shapes. We also have manufactured shapes and cross sections that are part of the database. And we have rods. So, if you had post tensioning or something like that, this is where you can choose different thin rod types. But we want an NDS shape. So I have no idea what size. Well, I could probably guess. I'm going to guess that this beam is going to work as maybe a 4x10, but you have glue lambs to work with. And you also have, PSLs, other manufactured lumber, but I'm going to guess a 4x10 to start with here. I'm going to choose my material, Doug, for large number 1. You can change the angle of rotation if it happens to be flat use or something like that. You can rotate it, and then you have your check boxes that go along with the NDS design code. And then you have just some other little features that are graphical for the way the DCRs would be colored. So I have my definition here. I'm happy with it. I just click out here, and here's my cross section all defined. And then I'll click the paintbrush to assign it. And since I had the beam already selected, it went ahead and assigned it to this one entity. So 4x10 assigned to one entity. And again, I can override layer colors and see that if I had different types, they would have different colors and things like that. The other thing let's see, there was one other thing that I didn't want. Oh, yes. So we can have labels as part of our frame element type. So I type MO, bring up the modify properties sidebar, and this has all kinds of options that you'll want to reference. You can put hinges at either end to make this sort of a pin member if you wanted to. This is the most important thing, probably. The unbraced length will definitely affect your capacity. So if you have a beam that's braced, you can always click on this label and you can get an explanation here. So this is the unbraced length, and we want to enter 0 if it's fully braced, or -1 if it's the entire element length is unbraced. And then there's something in between here, and you have the 2 axes for bracing. For my case, I'm going to assume that this guy is fully braced, so I put in 0 for both of those. The program does large displacement, so you can do cable analysis with this program, and we'll if we have time, we'll get into a concrete beam analysis where you can do creep and things like that. So there's other features for that. Let's say that if this was a rod, we could put in some pre-strain, and you can do pre-stressed concrete with this pre-strain loading. And then this is where the load sequences can come in. You can ignore entities for a certain part of the load sequence. Say, you have a column that doesn't show up in the first part of the dead load, and then it shows up for live load. You can do some fancy things with the load sequences there. And then in the results section, you can decide if you want this to hide graphs or hide the graph labels. And later on, we'll get a DCR log and see how the beam is performing. And then there's the standard geometry things here. I wanted to show that you can put a label on this, so I can put the length of the beam as a label, or I can put its cross section, its element model as a label, and then that label can be moved around if I wanted to. And then of course we'll get to this. We're going to tag this entity in a second so that we can look at its results. Okay, so my analysis is ready to run. How do I run the analysis? The easiest way to do it is to type F5, and that ran the analysis, and you see it's plotting actually the deflection of my beam right there. The other thing that you'll probably want to do is bring up the structural analysis options. So I start to type OPS, and there's a structural analysis options sidebar that comes up. And in this sidebar, you'll see a lot of important information. You'll see whatever models are part of this layout. So you can have multiple. The program basically generates models as you draw and connect things. So in this case, we have just the one model. And when I click on the list, it draws a box around the model. You can bring up the model dialog, and you can see information about convergence. This is a very simple model it's very linear, elastic, and so there's not a lot of useful information in here, but you might have something that's not converging for some reason. Maybe you're trying to do a buckling analysis or large deflections or a concrete beam or something, and you're not sure why it's not converging. This might give you some helpful information. It just gives a log of the analyses that are being run. This is where this is a button where I would click to analyze. If I wanted to run the analysis instead of pushing F5, you could push that button there. And then you can also auto analyze, which means that if I check that box, then every time I change the model, it will rerun the analysis if the model's valid. Okay, so then right now you see this checkbox view results. So it's viewing results, and that's why it's showing the 0.53 inches. I'm going to unselect this. If I uncheck that, then I can go back and see the loading and the support conditions and all that. So again, I can toggle results on and off this way. One thing to be aware of is if you're viewing results and then you want to change something about the beam, if I move this down, it's not going to take the loading with it because the loading is not visible. So if you want to edit something, you should go and uncheck the box that says view results. Okay, and so then we have a bunch of different drop-down menus. If I am viewing results, I can choose which load cases to view. So this would be showing actually all the deflections of all the load combinations and sequences that I've run, or you can just look at individual ones like this, or you can macro select them by, say, context ASD. So this automatically selects all the load combinations that were ASD. Model visibility, this determines whether I'm going to show the deformed shape and the displacement scale, and whether I want to show displacement labels and things like that. Loading, I can maybe show the factored loads and the reactions, and maybe I'm only interested in dead plus live, so there's not so many numbers showing up. And then we can determine other frame element results that we want to plot. So right now I'm plotting the display shape, but maybe I'm only interested in the moment. I uncheck the display shape and then I show the moment diagram here. Maybe turn off the loading like that. So now I'm seeing the moment diagram. Maybe I also want the shear diagram. There we go. Now I'm seeing the moment and the shear diagram in one plot. And maybe I want the DCR. And maybe I want to color by the DCR. So I see the DCR is too high. My beam is not working. 4x10 was not a great guess. and I'll need to go back and change that if I want to get my beam to work. A few more analysis options here. These are convergence options that are only going to be applicable if you're running a large displacement analysis or some sort of failure analysis. But these are the convergences that dictate the tolerances rather that dictate how the nonlinear analysis runs. And then for graphs, you have some features here, some scaling for the loads and the graphs, and then number format and units for display. So here's where you could pick, say, PLF rather than KLI or whatever. Okay, so that's how the analysis works in summary. Any questions? I'm going to keep going. There's a lot more features to talk about, but I want to make sure that we're all on the same page. So any questions so far? Nope. Okay. So if you are doing this sort of analysis and you wanted to, you're actually doing something for production, you would not want to view results this way. This is sort of nice for getting a quick look at what's going on. But if you're doing something for production, you'll want to have, you want to see all your moment diagrams and everything all in one place. And you'll basically want to see if the beam works without having to check this box back and forth. And so what we would do for that is we have a special command, viewport model. And so I start to type viewport model, VPM. Okay, so this is a very powerful command. When I click that, it shows all of the diagrams all at once so you can see the extents of everything. And it's asking you to draw a rectangle around your model. So I draw this rectangle here. And then it brings up a form where you can choose which results that you want to display. And what it's going to do is it's going to generate a viewport for each of the types of results that you're interested in. So for loading, let's say I want factored loads and reactions for just the dead plus live case. I want my deflections. I'll use all of the ASD load combinations for that. And then for my forces and everything, I'll use LRFD load combinations. And I want the DCR, demand capacity ratio, and the moment and the shear force diagram. And I click OK. And you see what it did is it generated now these 5 viewports. And it's asking me where I want to put them. And so by default, you just want to put in the angle constraint and just drop it down because it's going to put it directly below your model, or you can put it to the side if you want it to go off to the side. I'll put it to going down here. And then you have the option of scaling it, but I would just usually just push the enter key so it scales it to the real size of the beam. And then I'll close some of these things so I have a little more space to work with. And so now you see all of the results all in one place. I can see my loading for the dead plus live case that I asked for. I can see my deflection diagram for the ASD, so that's going to be the worst deflection under ASD load combinations. The DCR, this will be the DCR for any of my LRFD load combinations. And then my moment diagram for all the LRFD combinations and my shear force diagram. So it's all plotted all at once. It's on this one sheet, and it's ready to go, except for that I need to figure out why my DCR is not working. I can figure this out in a couple different ways. I'll type MO on this viewport. So now this is a viewport. We haven't really talked too much about viewports yet, but the viewport has special features. It allows you to look at a different layout or a different part of the same layout through the viewport. And so this viewport is looking at this model, and it's got some filters for what's displayed. So for example, it's overriding layers. And it's freezing. When I did the viewport model command, it freezes a bunch of layers that we don't want to see. Also, it's choosing different load combinations that we're interested in based on their context. And then it's choosing the results. Now, I wanted to see this DCR control here. And for some reason, this label has not been working. I have to go back and figure out why. It's supposed to show what is the controlling thing, whether it's moment or shear or whatever. So I have to go and review why that's not displaying anymore. But anyway, so this viewport is where you can control. I'm sorry, this little list here is where you can control what results are plotting through the viewport. Now, if I want to see more details about how the analysis, how the demand capacity ratio is calculated, I can select my frame element and I can click this button, clip DCR log, or I can just start to type DCR. And then I can look at all these analysis cases, or let's say I just want to look at this one here to start with. I bring up the DCR log here in this little form, and I can go through all the assumptions that the program is making that generates its capacities. And I go all the way down to the bottom, pull this over slightly, and I can see what the controlling DCR is all the way along the beam. And I can see, where my controlling DCR is for the entire beam right here. It's the one with the largest DCR, 1.6. It says that's PM. What I see here is that basically my moment is got 182. You'll want to look at the beginning of the file to see what the units are, but they're probably kip inches in this case. And then I can look up further up here to see, well, if my demand was 182, what was my capacity? That's what I'm really interested in. So my major axis bending stress capacity is it says 2.07 KSI, so that's it. That's a stress. And I would need to convert this to a moment to see how that compares to this moment demand here, 182. Down at the bottom, it's saying here what I have is an ultimate stress of 364 KSI compared with my capacity of 2.07 KSI. So that's really, this 2.07 is what's listed up here. And so this is what's controlling the design. And this gives me hints about what I need to do in order to improve the thing. Clearly the 4x10 is not working, and I can see it's not working by quite a bit, almost a factor of 2. So then I can go back into my frame element type, and I'm going to guess that I'm not going to be able to get this to work with a 6x10, and I'll probably want to do some sort of PSL, maybe 5.25 by 7. What else do I have to work with here? Let's do this guy, the 5.25 by 11.875. I click that. I click out of there. It has now updated that element type. I rerun the analysis, F5, and now I have a DCR of 0.3. So now it's working quite easily, and everything has been updated. Let's say later on you have to design for a point load. So I'll put in a point load, PLD point load. I put that on here, and then the analysis dumps because it's not valid anymore. I have a load that is not part of a load set. If I go to the structural analysis options, I see this model says analyze to validate, so it hasn't been analyzed yet. I click analyze now, and it says model invalid, and I wonder why. So I double click on this, and I can read load invalid, not a member of any load set. Okay, so I know that I have a load that's not a member of a load set, and I got to work that out. So let's say my point load here, I'll just make a point load. So my P, call it, will be a dead load, and let's say it's it's a 10-foot by 4-foot area of W dead. So I'm just putting a point load on there of 1.4 kips. And then I double click on my point load. I put in PD like that. So now I have my dead load in there. I need to assign it a load set. I can do this 2 ways. I can go here and do the paintbrush like I showed earlier, or I can go in the modify properties sidebar and find where the load set is located in this thing, and it's under expression. I put that on dead. And then now that thing should be set. It says the model is invalid. I can click analyze now, and we see that it actually did analyze this time. And I'll just for fun, I'll turn on auto analyze, and we'll show this here. So now it reran the analysis with this dead load. The beam is still working, but let's say the dead load moves over a little bit. I can just I'm pushing the arrow key, by the way, control arrow left. And I can move it along and kind of see how the moment diagram and everything is changing, and the DCR is changing as I go along. Maybe somebody's walking across the beam and I'm interested in that. So that's how the auto analyze works. And that's how the point loads work. Okay, so once this is all done and you're ready to go, we would do a print area set. I have my page here, Control P. And I always take a look at the print just to make sure things look good. And that's looking fine to me. And then I can go ahead and make a print of this and send it off. Okay, any questions, anything anybody wants to discuss?
Mike, can you display some query results like the...
Oh yeah, thanks for reminding me. Yeah. Let's say, so we have all these diagrams and everything, that's great, but let's say we want to actually query results like Natalie was saying out of the entity. So that's done by making a tag first. So I'll start to type tag, and I'll set the entity tag for this frame element, call it my beam BM, like that. And then you'll see now this beam has two labels. It has the entity tag BM, and then it has its element model right there. And I can make an expression, and I can get results for that beam through a function called elRes. And there's actually many different functions you can see here. They all start with L for element. elEnv would give me the envelope of a bunch of different load combinations, and then res would give me the result from a single load combination. And then the rest of these are sort of built off of that. So you have res, so the result at a particular location, at a particular step. So if you're doing load sequence and you're trying to figure out what's the result at a certain load step, you can get it that way. Last converge. So if you have a buckling analysis, you want the load combination or the step that converges last. But most of the time we're interested in this elEnv. So this is going to be the envelope function. And when I look at that function, I see that it has to start with 3 arguments. And then there are also 3 versions of this, which will have additional arguments. So the first version is going to take the entity and the context and the result name. And then the next version would add to that an envelope type. And then lastly, we would have a different way of identifying the elements. So instead of having a tag, you could specify the layout and the handle, which is sort of an older school way of doing it. But let's say we go back to the basic version of this, and the first thing we want to do is enter in the entity reference. So that would be the symbol BM. And now it's asking for context. And so a list comes up that helps you type in what you need to type in. If you're looking for sort of like a moment demand, you probably want anything that's LRFD. So that goes in quotes. I double clicked on that. And then it asks you for what result name you're interested in. There are a lot of different results that you can get. Let's say, for example, we want the moment, the maximum moment. So, and we don't care about the sign of the moment, so that's why we want abs, so absolute value. I push the request for value operator, and I get this moment 234 kip inches, which you see matches with my diagram there. So what it's doing is it's going through all the results in that element for all of the different load combinations that are LRFD, and it's pulling out the maximum moment. The explanation of all those different types of loading, I don't know if you noticed it when I was going through here, You can type F1 and search for frame element for detailed descriptions. So we haven't really talked too much about the F1 help, but this does have a searchable help where you can click on it starts to type something in and it searches for topics and you can find what you're looking for here. And so these are descriptions of the different results types that you could reference.
Awesome. Thanks.
You're welcome. So I think I don't know if there are no other questions. I think we'll probably go ahead and wrap it here. And what we'll do is we'll pick up next time with maybe some other types of analysis, maybe some concrete beams or some cables or something like that.
Great. Does anybody
Okay.
have any specific requests from this room? No?
No? Okay. If
Awesome.
if you have one along the way, feel free to let us know, and we'll get the next tutorial scheduled to address some
Yeah,
more
just
topics.
one quick
Oh yes.
question.
Mm-hmm.
How to flip the load direction, like if it's a column or something and the load is
Yeah.
vertical or
Yeah.
horizontal, right?
Yeah. So the load has an angle associated with it. If I type MO, um, and probably in geometry here. You see there's this load angle right
Okay.
now. It's at -90, and you can rotate it just like any other entity. So I can, I click the grip, I hit enter twice for rotate, and now I put the load at this off angle, and it reanalyzed it right away.
Yeah, okay. Okay, thanks.
Yeah, you're welcome.
Thanks, Mohammed.
Any other questions before we wrap?
All right. Thanks everybody for joining us. I'll send you guys the summary notes and a link to the recording.
All right. Thank you so much.
Thanks, guys.